Hey everyone, welcome back. In today's video, we're going to talk about how to find inverse functions specific to logarithms and exponentials. I'm going to split it up into two parts, one for exponential functions and one for logarithmic functions. So without further ado, let's hop right into it. So before watching this video, you should have watched the Edpuzzle that gave you a recap on how to find inverses. When we started out this year in Unit 1, we talked about what an inverse is and how to find one, and some key features of inverses. So after you've watched that, you should be watching this. And before we hop into actually finding inverse functions, it's important that we recap and think about the things that we know about inverse functions. So I'm just going to make a little list of key things that we know about inverses. So what we know about functions that are inverses is that x and y swap places. So x and y physically swap places. Now, if we think back, x values are possible domain values, and y values are possible range values. So if x and y swap in the equation, that must mean that our domain and range swap for our inverse function as well. And since x and y swap and the domain and range swap, we also know that if I were to graph it, the graph of inverse functions are reflected across the line. Can you remember what it is? What line does it reflect across? Yes, it is the line y is equal to x, that diagonal line. Y is equal to x. And if we think about it, this makes sense. The algebra behind finding an inverses means that we're going to have to swap x and y. The domain and range have to swap. And in order for it graphically to swap, we would have to flip across this reflection line in order to do the most basic thing that inverses do, inverse functions do, which we know that inverses undo each other. And we have seen this while we were solving exponential functions or solving logarithmic functions, right? Think about it. Just like addition undoes subtraction, and just like multiplication undoes division, logs undo exponentials, and vice versa. So we know if addition undoes subtraction, then also the reverse direction holds true. Subtraction undoes addition. And if multiplication undoes division, similarly division undoes multiplication. And if logs undo exponentials because those functions are inverses, then exponential functions undo logarithmic functions. So these are some key pieces of information that everything's going to start to come together as we find inverses, as we graph these functions, and stuff we have to keep in mind while we are solving and finding inverse functions. So to start us off, I figure why not talk about inverse equations for exponentials? We just finished solving exponentials, so let's start with exponentials. So our goal for this problem, or for this area of the lesson, is that we are going to solve for inverse equations. And the way that we're going to solve for inverse equations is based upon an equation given to us. So in this section, we're going to talk just about exponential functions. And specifically, given a function f of x, our goal is going to be to find the inverse equation f inverse of x. Now, it's important to note that this notation means f inverse of x. This is not a negative exponent. So how are we going to solve exponential functions? How are we going to go about this? I thought you'd never ask. Okay, so what we're going to do when we solve exponential functions is just like we solved for inverses back in unit 1, way back when. We're going to first, after we have an equation, rewrite f of x as y. Then we're going to switch the variables. Remember, x and y switch. And then we're going to use inverse operations to isolate the exponential function part of our equation. Once we have that, it's kind of like solving for an equation. We're going to take the log of both sides and then continue in our journey to solve for y. Lastly, we would convert it back to inverse notation, writing the equation as f inverse of x. So let's do an example. Suppose we are given f of x is equal to 3 to the x minus 1. Notice that this is an exponential equation. My base is 3, my exponent is x, and I'm subtracting off 1. And our goal is to find the inverse f inverse of x. So we're going to follow our step-by-step procedure. Step 1 says to rewrite f of x as y. So step 1 says to rewrite f of x as y. Okay, sorry, I kind of made a mistake here. Mistakes are normal. Y equals 3x minus 1. Cool. Then step 2 says to switch x and y. Now remember, I'm just switching the variables. Everything else remains exactly the same. So y becomes x becomes y. Step 3 says to use inverse operations to isolate the exponential function, which means I want the exponential function by itself. I need to get rid of this minus 1. What inverse operation might I use? Well, I'm just going to add 1 to both sides. Why the heck not? So I could add 1 on the left, and whatever I do on the left side of an equal sign, I absolutely have to do to the right. I end up with x plus 1 equals 3 to the y. And now that I've used inverse operations to isolate the exponential part, I can move on to step 4, which is to take the log of both sides. Now remember, inverses and logs are, logarithms and exponentials are inverses. So I can't just take any log. I need to take a log with the same base as the exponential. So the base of this exponential is 3. 3 to the y is my exponential part. I'm going to take log base 3 of both sides. When I do this, since logs and exponentials undo each other, I end up with log base 3 of x plus 1 equals y. So I already hopped all the way over to 5 just because I used the correct logarithm to solve for y. And if there were any other steps that I needed to take to continue to solve for y, I would do that. If I needed to use any other inverse operations like subtracting, multiplying, all of those things, then I would do so. And lastly, we would rewrite our function instead of y equals log base 3 of x plus 1. We want to use the appropriate notation of f inverse of x is equal 2 log base 3 of x plus 1. That wasn't too bad, right? Sweet. Let's try another example of finding an exponential function. The inverse of an exponential function. So this was 3 to the x minus 1. What about, I'm actually just going to move this over here. What about if our next example is find the inverse of f of x, given f of x is 3 to the x minus 7. Almost exactly the same. Remember, step 1 says to rewrite f of x as y. So we're going to say y equals 3 to the x minus 7. Step 2 says to switch x and y. So x equals 3 to the y minus 7. Step 3 says to use inverse operations to isolate the exponential part. So in this case, I'm going to add 7 to both sides. I end up with x plus 7 equals 3 to the y. Step 4, once it's isolated, take the log of both sides, but not just any log. Nope, we've got to take the log base 3 to undo 3 to the y. So log base 3 of x plus 7 equals log base 3 of 3 to the y. Oops, almost ran out of space there. Again, since they're inverses, they undo each other. We are left with log base 3 of x plus 7 equals y. And lastly, we want to write it using the appropriate notation. So f to the little superscript -1 means f inverse, again, of x, because we're dealing with variable x, is equal to log base 3 of x plus 7. I'd like you to pause for a second and tell me what you noticed about this problem-solving process. What makes sense in terms of how we were solving for exponentials and log functions? Thanks so much for reflecting. Let's do 2 more examples of solving for exponentials, okay? Let's increase the difficulty just a little bit for solving for exponential inverse equations. So here's our next example. What if I gave you the function f of x is equal to -2 to the x over 4? And your directions are to find f inverse of x. So we have f of x equals -2 to the x over 4, and our goal is to find f of x. Again, recognize that this is an exponential function. The base is 2 and the exponent is x, the variable x. So we're still going to use our step-by-step directions to solve for an exponential function. Step 1 says to write f of x as y. So we're going to say y equals -2 to the x over 4. Step 2 says to switch variables x and y. So x equals -2 to the y over 4. And even though it feels weird and it's kind of more complicated, let's just continue following our step-by-step procedures until we're able to get to a place where things feel a little bit more familiar. Even though problems can increase in complexity, the problem-solving process should remain the same. So step 3, we're ready for it. It says use inverse operations to isolate the exponential function. So we want to use things that undo each other to get the exponential function alone. And sometimes a strategy I like to use to make sure that I'm isolating what I want is I will find the exponent and look at the base and circle it. So I want to get -2 to the, or I'm sorry, just +2 to the y alone. So I've got a couple obstacles in place right now. I need to get rid of this denominator of 4, and I recognize that this is dividing by 4. This is taking my exponential equation and dividing it by 4. So to undo that, to use an inverse operation of division, I could multiply both sides by 4. Right? Doing so will eliminate and cancel my denominators. And whatever I do to one side of the equal sign, I should do to the other side of the equal sign. Otherwise, I'm not maintaining equality. Now I've got this pesky negative number. I could also multiply by a negative 4 on both sides. And if I do the negative 4, a negative times a negative, those guys cancel each other out. And I'm left with negative 4x equals 2 to the y. Voila. I finally have used my inverse operations to isolate this exponential function. Now I'm ready for step 4. And step 4 says to take the log of both sides. So step 4, I'm going to take log, but not just any log base 2. Since the base of my exponential is 2, the base of my logarithm should also be 2. Since logarithms and exponential functions are inverses by nature, they undo each other, just like addition and subtraction undo each other, multiplication undoes division. So what happens is I end up with log base 2 of negative 4x equals y, and I officially have solved for y, right? Y equals something. Y equals a specific thing, right? A specific function input. So all that's left to do is to rewrite this using my function notation, using f inverse of x, stating the inverse of this original function is log base 2 of negative 4x. Look at our original function. Our original problem that we set out to solve, all the way up at the top. Look at this guy. F of x is equal to, 2 to the x divided by 4. And compare it to f inverse of x is log base 2 of negative 4 times x. What do you notice that seems like a connection between the original function f of x and the inverse function f inverse of x? What do you notice? Look specifically at the numerical values of f of x and the inverse values of log base 2 of negative 4x. Can you make any connections? What do you notice? And what do you wonder? Awesome. Thank you for noticing and wondering. Now, lastly, we're going to do one final example of solving for inverses with an exponential function. And again, kind of like we've been doing with each problem, we're going to amp up the difficulty just a tad. So we had f of x equals negative 2 to the x divided by 4. In this third and final example, we are going to have our function f of x is equal to negative 2 to the x plus 3 over 4, and our goal is to find f inverse of x again. So let's grab our step-by-step procedures, our list of how we find exponential functions, and go along because we've definitely increased the difficulty. So step 1 says rewrite f of x as y. So y is equal to negative 2 to the x plus 3 over 4. Step 2 says to switch x and y. It's the most important part of finding an inverse. Otherwise, you're just finding not an inverse. You're just kind of doing some algebraic manipulations. X is equal to negative 2 to the y plus 3 over 4. And now, step 3, use inverse operations to isolate the exponential function. Find your exponent, find the base, put a circle around it, a box around it, highlight it, whatever works for you, that we're not going to stop using inverse operations until 2 to the y is alone. All right? We're not going to stop using inverse operations until 2 to the y is alone. Now, this is pretty similar to the last problem. Notice that I just added an additional operation in the numerator. So we still need to get rid of this denominator. We still need to get rid of 4. And as a matter of fact, we still need to get rid of the negative. So I can multiply both sides by -4. To get rid of not only the 4, but the negative as well. And whatever I do to the left-hand side, I must do to the right. I'm sorry, you couldn't really see that. That said -4. Okay, so if I do that, I have -4x equals 2 to the y plus 3. I'm almost isolated. I'm almost completely isolated. Notice now I have to get rid of 3. So the inverse operation of addition is subtraction. And whatever I do to one side of the equal sign, I better do to the other. So on the left-hand side, I have -4x minus 3 equals 2 to the y. Now I have officially isolated the exponential function. Next step is to take the log of both sides. To take the log of both sides, it's not just any log, it's got to be a log with the same base. So we're going to take log base 2 of -4x minus 3 is equal to log base 2 of 2 to the y. Since logs and exponentials undo each other, they are inverses, we are left with y is equal to log base 2 of -4x minus 3. And the last thing to do, notice that I've solved for y equals a specific something, a specific function. All I have to do is use my inverse notation. F inverse of x is equal to log base 2 of -4x minus 3. What? Awesome. In the next video, we're going to do the same type of process, except we're going to start with a log function and work backwards to get the exponential function that should be its inverse. See you then.